So today I'd like to solve this problem. So we have refrigerant 134A is working fluid in a vapor compression refrigeration cycle with two evaporators. So the refrigerant goes through the compressor, then it goes through one condenser. So one compressor, one condenser, but we have two evaporators. In order to have two evaporators, we have more than one expansion valve. So you can think of this as the pressure, the high, the pressure, the medium, and the pressure, the low. And we have an expansion valve that drops it from high to medium pressure, and then from medium to low pressure. And then we still need another expansion valve to drop it when it comes out of that first evaporator from medium back to low pressure. So we have three expansion valves, and we have two evaporators. Okay. The saturated liquid exits the condenser at 34 degrees C. So it's saturated liquid, 34 degrees C. And we've numbered the states already, so that's state 3 coming out of the condenser. The refrigerant in the evaporators are at 0 and negative 20. So this is 0 degrees C, negative 20 degrees C. And saturated vapor is exits. That's a standard assumption that comes out of the evaporator. It could come out slightly superheated out of that evaporator. Normally it is a little bit of superheat, a 1 or 2 degrees F, or not much superheat. But here in this problem, they're coming out saturated vapor at 0 degrees C, the intermediate pressure evaporator, and then negative 20 degrees C. The first evaporator has a refrigerating capacity of 0.9 ton. Okay, so ton. What is a ton of refrigeration? 211 kilojoules per minute. So we can convert that rate of heat transfer that's given. This one is what's coming in to the first evaporator. The rate is 0.9 ton. Which, when we convert it, let me take a look at my numbers here, is 3.165 kilowatts. And then what comes in to the refrigerant in the second evaporator is 0.8 ton, which when we convert it is 2.813 kilowatts. Now, for part A, they ask, what is the mass flow rate of the refrigerant flowing through each evaporator? So we have an m.1 going through the first evaporator and an m.2 going through the second evaporator. And if you think about it, what comes through the condenser, isn't that the sum of m.1 plus m.2? Yeah. And what goes through the compressor, isn't that the sum of m.1 plus m.2? Yes. So what's happening here, they really don't show it in the illustration. What happens right here? Yeah, it's simply mixing. Oh, we could say that's an open feed water type heater, but all is taking two fluid streams, mixing them. So the two refrigerant streams are mixed, and then it goes into the compressor. So they want to calculate m.1 and m.2. How would we calculate m.1 and m.2?
First law analysis where they mix.
Well, let me do this. What we have is q.1. And so q.1 is a product of m.1 times a change in the enthalpy. And the change in the enthalpy is for the first evaporator, is it not? So that's, where did we get that equation? First law analysis of that first evaporator. And it'll be H on the outlet 5 minus H on the inlet 4. Do you like that equation? Could you have gotten that equation without me telling you that equation? All right. And then this, so basically, if I want to calculate the mass flow rate going through the first evaporator, I really already know Q dot. I just need the enthalpies at the state, inlet and outlet state. Likewise, if I want to calculate the Q dot, I have Q dot 2 is equal to M dot 2. That's what I want to calculate. That's equal to, if I analyze the second evaporator, H8 minus H7. So the answers for part A really come from getting the enthalpies. And it's really hard to get the enthalpies, so let's do it right now. We'll set up a table, and we'll say, here are some notes that help me remember how I fixed that state. And then this is the number of the state. And then this will be the pressure in kilopascal of the state, the temperature in degrees C of the state, the quality of the state, the enthalpy in kilojoules per kilogram of the state, and the entropy in kilojoules per kilogram Kelvin of the state. So the key properties are enthalpy and entropy, primarily enthalpy. So what we have to do is, how many states? They gave us all the states, true? And there's state 1, then there's state 2, there's state 3, 4, 5, 6, 7, and 8. So we have 8 states. And this is where you can't solve for state 1, everything in state 1, and then move to everything in state 2. And you have to really look at the problem and figure out, what can I solve for? What can I start putting down? I need 2 properties at each state to get the other properties. And so you probably key in on which state.
3.
All right, that's the last one for you today. Got it. All right, so state 3 is it. So if we take a look at state 3, we would say, my notes, this is what helps me, is I would say it's saturated liquid, and I know the temperature. Let me just put it as T here. And so I would come over here and I'd put 34 degrees C. How would that help me get H at 3, or S of 3? That's H of F at that temperature. And if I need it, I really don't think I need it, but if I needed it, I can get S of F. And then what is the quality? Saturated liquid? 0. And what about the pressure? That's the saturation pressure. You know, that's our high pressure. That's our high pressure, isn't it? Okay. Maybe you put this as pH right there, the high pressure. Okay, what is the next state? Just trying to organize the information given in the problem statement that we know a lot about. Somebody over here. 4. She says we know something about state 4. Well, how about state 5? That's even easier, isn't it? So state 5, what do we know? That it's saturated vapor, and we know the temperature. So we put in, oh, it's 0 degrees C. Can I find the pressure at state 5? Sure. That's going to be my intermediate pressure, and that's the saturation pressure of refrigerant 134A at 0 degrees C. How about the enthalpy? H of G at that temperature, S of G at that temperature, and equality is 1. Does that make sense? All right. One more state, just organizing the given problem information. Which state is it? 8. You're exactly right. 8. So we take a look at 8. We know that it's saturated vapor at that temperature. Let's say the temperature is negative 20 degrees C. And so knowing that, we get the low pressure, which is Psat at negative 20. It's saturated vapor, quality 1. We get H of G and S of G at that negative 20 degrees C. Now, what I like to do is maybe fix all the pressures, because I know there's only 3 pressures in this whole system: high, medium, low. So let's take a look. What is pressure? Which states all have the low pressure? That's right. So this is PL, 8, 6 PL, and 1 PL. They all have the same pressure. Does 1 have the same pressure? 8. What number is this right here? 1. Did I put down 7? Oh, also PL, 7. That's right. 7. Low pressure, low pressure, low pressure, low pressure. How about the intermediate pressure? Just 4 and 5 for the medium, intermediate pressure. And then how about the high pressure? 2 and 3, so pressure high. So we have all the pressures figured out, and we have a number of the states figured out. We're really looking for the enthalpies. Might as well flush out this whole table. Again, this is one of those where you don't start at the top and just work completely to the bottom. You just don't. Okay, but we want to try to work in that order. If we look at it, if we try and say, well, can I get from information about 1 and maybe get to 2, go through that compressor? Well, I don't know a lot about 1 yet, and it's not going to help me get 2. But how about if I start at 3 and I work down to 4? Sure, now we know, okay, I can do that one. Probably some of you said, once I know what 3 is, I can tell you what 4 is. But you really needed to know the pressure at 4, and that was determined by the pressure at 5. So anyway, so we know that the pressure and the enthalpy fix state 4. So this enthalpy at 4 is equal to the enthalpy at 3. You just bring that down. It's isenthalpic flow through that expansion valve. And the intermediate pressure, so we would go and we would get the temperature, and the temperature, from your experience, what do you think the temperature is at 4? It's because it's saturated liquid. I may have in my mind an image of a temperature entropy diagram, and I just draw it like this, and I'll put 3 lines of constant pressure: a high pressure, intermediate pressure, and a low pressure. And where would be state 3, it would be at high pressure at saturated liquid, wouldn't it? And if I'm going to put it through an expansion valve and drop to that intermediate pressure, where is it going to end up? In the dome with some quality, 20%, 30% quality. That's right. And so right around here would be state 4. So its temperature is, you can check it. The temperature at 4 will be the temperature at 5. Because where's 5? Isn't that coming out as saturated vapor? Yeah, saturated vapor coming out. All right. Now that you know state 4, you know where state 5 is. Let me skip state 6 for a minute. How about 4 to 7? 7, wouldn't that be just a continuation kind of that way? Does state 3, 4, and state 7 all have the same enthalpy? Yeah, they all have the same enthalpy. So this is also equal to H3, which is H4. So H7. So the information at state 7 that fixes it is the low pressure and the enthalpy. So I can work through the rest of those. I can get, if I want, the temperature. The temperature at 4 we know is 0. The quality is, I don't know, maybe 20%. I'm just going to throw a number out. The next slide has the exact number. Maybe it's around 20%, something like that. And then the quality here would be like 25 or 30% because it has to continue to go over, increasing quality. And so it would be at negative 20 degrees C. All right, now let's talk about state 6. Have you taken saturated vapor and put it through an expansion valve? No, normally we take saturated liquid and put it through an expansion valve, don't we? So it makes us think a little bit. It's saturated vapor. Where is the inlet to the expansion valve? State 5. Where does it have to end up on my TS diagram? Doesn't have to end up at the low pressure. This is the intermediate pressure. This is the high pressure. So where is it going to end up? At that low pressure. Will it be superheated? Will it be saturated vapor? Will it be two-phase liquid vapor mixture? Slightly superheated. So it's going to come down and we'll have 6, I'm going to exaggerate it, but there's 6. All right. Now, the 8.
For sure that it's superheated.
The entropy has to increase.
How do you know it's that much though?
You would have to run the calculation and find out. You would have to compare the actual entropy. The other is you would look at the entropy at state 8, which is right here. And basically, if I look at, actually the enthalpy will do it, not the entropy. Entropy is definitely going up, but the enthalpy, you can see that it's higher because it's isenthalpic. So enthalpy at 5 is higher, and that's equal to enthalpy at 6, and it's higher than at 8. So you have to work on it. I know it's probably, I said it too fast.
So you're just checking the tables?
Checking the tables, yeah. We have two pieces of information at fixed state 6. What again are they? Enthalpy. Oh, I didn't write it down, did I? It's the pressure and the enthalpy that fixed state 6. It's isenthalpic. So H6 is equal to H5. And when you check, you're going to find that H5, or H6 now, is greater than H of G, saturated vapor, at that low pressure, which is equal to H8. So it's going to have a higher enthalpy, hence it has to be slightly superheated. Okay, that helps us get that enthalpy at 6, and the enthalpy at 8 is known. What about, at this point, we really can't get enthalpy at 1 and enthalpy at 2 until we finish solving part A, because we don't need the enthalpy at 1 or 2, we just need it at 5 and 4 and 7 and 8 in order to solve for part A. We have to know those m dots. So this is a really tricky problem. It's like I got to go halfway through the table, stop, calculate the mass flow rates, then throw that back in to help me calculate H1. Okay, so knowing these values of H, you can calculate m.1 and m.2. It's on the next slide. Now the question is how do I calculate state 1? Yeah, you have basically control volume for the mixing, 2 inlet streams, 1 outlet stream. And the energy balance, I don't know where to write it. I've been fighting for space here, trying to be neat and orderly. But if I wrote the energy balance, I'd have the mass flow rate coming in through the first evaporator times the enthalpy at 6 plus the mass flow rate coming through the second evaporator times the enthalpy at 8. That must equal to the mass flow rate going 1 plus 2, which is the total coming out, times the enthalpy 1. And guess what? In that equation, once I calculate m.1, m.2, there's only one unknown, H1. And so the H1 is calculated. So when I come over for state 1, it's that low pressure and the enthalpy that fix that state. And this is where I finally absolutely positively have to calculate the entropy, because I'm going to look at going through that compressor. So we'll calculate S as a function of pressure and enthalpy at 1. And then we'll say isenthalpic compression, so S2 is equal to S1. And we jump up to the high pressure, so pressure and entropy, S, fix state 2. What do you think is the state of state 2? Well, first of all, where is state 1 on this temperature entropy diagram? Has to be on that low pressure line, right? But where would the blue dot for state 1 be in comparison to 8 and 6? Right in between them somewhere. It could be 50-50 in between. It could be 40-60 in between. It'll depend on the mass flow rates, the relative. If the mass flow rate going through the first evaporator is a lot higher than the mass flow rate going through the second evaporator, then H1 will be a lot closer to H6. Right? All right. So basically H7, and you can tell then that 7 is slightly superheated when we put it through the compressor, perfectly up, and there's state, that's state 1, right? Did I say 7? Sorry. Over to state 2. How many times did I say state 7? No wonder you can't learn anything. I'm so confusing. All right, so there it is. So state 2 is going to be really superheated. You ready to look at the answers? So here are the answers for this problem. First of all, I did it in software. Just like I shared with you the Excel files for the add-ins that were based on the tables in our textbook, well, I also have built the Refrigerant 134 tables. You don't really need them for the project. If you want them, I can load them up there. You'll have to do the add-ins. Who wants them? All right, I'll load them up there. And so just like the thermo tables, and it's the same structure. Okay, once you did it for one property, you figure out how to just reproduce the algorithms. Well, here is the solution. So we found that the mass flow rate's a number, the mass flow rate's a number. Then I calculate the mass fractions. And for these numbers, I played with them a little bit such that they're about 50-50. You know, that's close enough to 50-50 split. If I would have changed the tonnage in one of the evaporators, oh, that would change the mass flow rate and the mass fractions. Anyway, the final answer is 1.67 kilowatts of power for part B is supplied to the compressor. Do all these values look good? Why did I color code this one, this one, this one? They were pretty much given. Yeah. So somebody comes in and says, no, it doesn't come out at 34 degrees C, it comes out at 36 degrees C. Well, I can change the code and it'll percolate through and it'll redo the numbers. Oh, I don't want this evaporator to be 0, I want it to be -5, and I want this to be -25. Okay, fine. It'll change, and that's the beauty of the software. You can see the quality. We talked about that quality coming after state 4, or at state 4 after the first expansion valve, about 25%. What does that mean? By mass, 25% of the refrigerant has quote-unquote flashed. It's gone into the vapor state, leaving, well, 24% more to be precise, leaving 76% liquid ready to evaporate. And that's what's going to provide that cooling. Because does the vapor change phase as it goes through the evaporator? No, the temperature at 4 and the temperature at 5 are the same. So the vapor is staying 0 degrees C as it goes through. But the liquid comes in and it's changing phase up to the vapor, and that's where you get the cooling, evaporating the liquid. Okay. Because you drop through the next one, you even find out, oh, it's closer to 35% quality. Meaning 35% of what started out up here is now flashed. And it's already vapor. And it's not going to provide the cooling in the second evaporator. The 65% remaining liquid will. All right. This is, the next slide shows you if you type the control tilde in Excel. So in Excel, once you've solved your design problem, right, copy it to another sheet, the whole thing. Don't try and do the formatting in the same sheet. And don't try and do it until you're really done. You don't want to do this more than once. It's a pain. But copy it to a new sheet, the whole thing. In that sheet, hit Control tilde, just Control tilde, and all of a sudden, boom, I can see the cells and all the equations. So you can see that right here, I typed in a hard number 34, I typed in a hard number 0, and a -20. But I then called PSAT as a function of temperature, refrigerant 134A, out of table A10, that's my syntax for this call, from the cell D5. Well, here's D, and here's 5. Oh, I just put that number right there. So I can see exactly what you're doing in your design. And anybody then can see, and you can share code a lot easier. And so you can see all of the logic. Let's say up here, remember it was pressure and the enthalpy of the mixture fixed the state? Well, I'm looking for temperature as a function of pressure and enthalpy. And luckily that algorithm was built. And then where is my pressure in cell, whatever that is, C whatever, C3 and then F3. So it grabs those. This is the equation for the mixing. The equation for the mixing uses those mass fractions, which are down here in cell F13, F13, as well as the fraction in F14. So hopefully you're familiar with the syntax for spreadsheets. All right. Any questions about that? What's my recommendation again? Do this once. Do this only after you're confident you're done, that you're not going to have to tweak anything. Because when you do it, you have to sort of grab this and move it back and forth to get it to fit on a page nicely. Because if you just hit Control tilde, all the cells won't show. You'll have to play with the formatting to actually make it look good. All right. So not only can you do it just with the tables by hand, or maybe with the help of some of the software add-in that is exactly matches the numbers in the table, the textbook, so you get a very warm, fuzzy feeling, right? That, hey, I'm doing the right thing. I do it by hand. I get to 5 digits, the same answer. You can also do it. I want to show you software that's available out there on the internet from the University of Alabama, and then also from NIST. To do that, what I want to do is I want to switch over and do it with the switch over here. So you would go out to the internet, and the first one is all you have to do is search for Excel and ME. It'll always go to that website, and when you go to it, it'll first in the pop-up is me.ua, University of Alabama, and then that's a website. You can go to that website. They have software for thermodynamics, heat transfer, thermal systems. It was all NSF funded, and so you can download this and play with it. It's very good software. I've used it for a number of years. You probably want the 64-bit Windows right here, and you probably do the all-in-one download, which gives you all the Steam properties. It's Xsteam. Refrigerant 134A, R22. It doesn't give you a whole, but what it gives you, it's very good at. It's very good at the refrigerant 134A. It's very good, but does it give you ammonia? No. Propane? No. But what it gives you is very good. The steam is very good. It also gives you other things, ideal gas and things, but I'm not recommending anything but the thermodynamics. Other stuff is good, but for this class, you don't have a lot of time to go exploring. The other one is you would just type in mini refprop. Refprop, but if you put mini in front of it, it's smaller, it's student version. And so you'll get to this boulder.nist.gov. You can click on that and basically read that it's a program, it's a sample version of the full refprop program. You can buy the full refprop if you want to spend a couple $100. It's cheap, actually. It's put out by the government, federal government. It's NIST, National Institute of Standards and Technology. They have offices in Boulder, Colorado. Great place to live, I'm sure. And so it's a teaching tool and an introduction of thermodynamics for you, the student. It contains a very limited number of pure fluids. Water, excellent. CO2, carbon dioxide, excellent. Refrigerant 134A, excellent. Nitrogen, methane, propane, hydrogen, dodecane. If that's a limited set, you should see the full set. There's a very long list for the full set. Very long list. And it handles mixtures as well. So mixture calculations of nitrogen with methane are the only ones put in here for the teaching purposes. They get the vapor liquid equilibrium data. But there's a bunch of other things that you can do. I mean, it's like state of the art, world renowned. Okay, it's the best. There are other software out there, but this one, I think they copy it. So basically, you would just click and download. Well, guess what? I've already downloaded it, okay? And so in the interest of time, I'm not going to do that, but you would save it somewhere, and then you would, after you download it, you'll get a little icon here, and then you can just start it up. So I do want to show you this. You can do the Excel add-in for the refprop. You can run it in MATLAB. You can run it in all sorts of software. You can run it in, you just name it the software. Python, they've got it. C, you got it. I think Fortran even. Okay, this is going to open, I think, or no, there it is. So let me do this. Don't pay attention to those screens. I'll get there. But options, just like a software you would want. What temperature do you want to work in? We'll work in degrees C, Kelvin. What pressure do you want to work in? And there's a lot of pressures. It's your choice. You can mix and match units. I like kilopascals, so I'll stay there. Volume, meters cubed, centimeter cubed, all of that. Liters. Similarly, so they have defaults to switch to one or two. You got to work on a mass basis, molar basis. It's just a bunch that you can select. That's just on your units. Properties. Do you want the pressure, the temperature, the density, the specific volume, the internal energy, enthalpy, entropy, specific heat, constant volume, specific heat, constant pressure, the low pressure specific heats, the ratio of specific heats. I don't even know what this is. I have to look at it some more. Speed of sound, compressibility factor, the Joule-Thomson coefficient, the quality. I've checked the quality in a few of these. The virial coefficients for different equation states, Helmholtz function, Gibbs function, heat of vaporization. So there's a lot of properties, as well as those are thermodynamic. You have transport. You want thermal conductivity, viscosity, kinematic viscosity, thermal diffusivity, Prandtl number, surface tension, dielectric coefficient. I know I'm boring you, but it's for even the student version for water. You've got a lot. Here is, let me see, where do they put derivative properties? So if you want the isothermal compressibility, volume expansivity, isentropic expansivity, all these properties and all the partial derivatives. All right, that's the chapter that I basically have to skip in this textbook to really go through thermodynamic relations. It's really more of a graduate topic. There's special properties, and this is the flow exergy. I don't know why they put it over here, but if you want to do exergetic analysis, you've got to find the flow exergy. And they should have maybe put it in the thermodynamic list, but that's wherever it is, okay? And then mixtures, I'm not going to show you those. Well, whatever. Let's go back. Go cancel. Now the substances. There's a lot to select, but let's go ahead and just select pure substance. They warn you that this list could be long, but you got the student version, and there's your list. So refrigerant 134A is the one, or water, etc. And then you would just say, okay, let's do it. Okay. And then you can calculate. And you can get a bunch of information in a table, make tables of properties, or at a specific state. If you go at a specific state, like say I want to put in, what are we working with, refrigerant? Maybe it was, I forgot my numbers. Let's put in that high pressure of 863 kilopascal, and the superheated temperature was around 50 degrees C. Boom. Just like you would expect. The software helps you. You can say, well, I know the entropy is 1.767, and the temperature is, I forget, negative 6 degrees. It tells you, oh, it's superheated, and there you go. Now you wonder why we don't show this to students in Thermo 1. Yeah, it's like, don't feed your young children candy for breakfast, supper, and lunch, you know, and it's like you can't do that. All right, then also it can give you plots. Do you want to plot temperature entropy, temperature density, temperature enthalpy, pressure enthalpy, all these plots, okay? The ones that I like to look at are pressure entropy and pressure enthalpy, or temperature entropy, TS, and pressure enthalpy. Well, what I did for this problem is I worked it up. It took me a little bit, so I got them in the right numbers, the same numbers in the line for the states that are there, which wasn't easy to do. But if you want, you can compare these numbers with the other numbers. They're not exactly the same. They're off, but they're close. And they'll give you the same final answer, mass flow rate and mass fractions as well as that. Also, I made some plots. This is a pressure enthalpy plot made there, and you can play with it. There's a lot you can do, as well as the temperature entropy plot. So, without spending more time in the software, I'm going to switch out back to our presentation. And here is the data for that software, refprop. You can sort of see the icon right there for all of the states. This was not easy to do. It was a little painful because it's usually not set up that way. And then what I would like you to do is I'd like you to kind of sketch the temperature entropy diagram and put on the states. I think I already did that, didn't I? Yeah, I did that. Basically, you can come back here to our little illustration right here where I put all the states. And you could put a line for the particular pressures for our problem, and then actually put little boxes within the software for this is state 2, this is state 3, this is state 4, this is state 5 coming out over here. Then it goes to 6. 6 goes this way. And then jump back, here is state 7 right there. This is state 8 right there. And then what was 1? It was a mixture at low pressure, and it was basically a 50-50 mix. It's halfway between roughly. I mean, it's entropy is going to be, actually, if it is perfectly a 50-50, it's a perfect 50-50 split right there. And then we go through the isentropic compression, and there you go. There's your cycle on a TS diagram. Okay, how about a pressure enthalpy diagram? This one I want you to do. I want you to look at it and say, well, we had a temperature of 34 degrees C. That was what's coming out of the condenser. We had a temperature of 49 degrees C. That was what came out of the compressor, so it was slightly superheated. Here is a temperature of 0 degrees C. That's the first evaporator. The temperature of negative 20, that's the second evaporator. And then the mixture at state, after that expansion valve, it was negative 6. Okay, so I want you to sketch a pressure enthalpy diagram knowing kind of these values of temperature and put the states on, okay? I'll give you a minute. All right, so this is what it looks like. Notice there was only 3 pressures. Everything's on that line or on that line or on that line. That's it. You just had 3 pressures, the high, the intermediate, and the low pressure. Now, it gets a little confusing down in here because we're coming out of that evaporator down here at state 8, and we come out of the first evaporator, state 5. We go to an expansion valve. Its expansion valve is isenthalpic, straight down, isn't it? So it's almost easier to find your states because you're having a lot of expansion valves and things are constant pressure. pH diagrams they like for refrigeration. So this is state 6, and then you just average the 6 depending how much, what's the mass fraction. It's 50-50 for this problem, and so that's state 1. And then the difficulty is we don't have a nice curve for isentropic process, but that's a line of S equal to constant. It's sloped and bent a little bit, and that gets you up to state 2. And then this is state 3, and then this was state 4, and this was state 7, right? 7 down there. So we're done for today. Thank you very much for your attention. I'll be here if you have any questions.